we're bombarding it with the alpha particle, producing a neutron, and the product nucleus is the curium particle. Okay. So make sure you're able to take a transmutation type reaction and write in the shorthand, or go from the shorthand to the full reaction. Okay. Particle accelerators is another way. Oh, look at that. Thanks. Good job, me. Another way to produce new elements. Okay. So the element with atomic number 117 was relatively recently produced. Does anyone know what the name of 117 is? Yeah, we have it listed as UUS here. It has a name now. Anyone? It's TS, and it's tennessine. Anyone from Tennessee? It's named after Tennessee because it was produced in Oak Ridge National Lab, which is in Tennessee. Here's Oak Ridge in this citation. Okay. I would also like to point out with this paper, there are scientists here from the US and from Russia, so this was a little bit of a different time, not that long ago, 2010. And so, let's see, the way they produced this was, here it is in the abstract, fusion reaction between calcium, and does anyone know what BK is? Not Burger King. Berkelium. Berkelium named after Berkeley. So Berkelium-249, which has atomic number 97. There we are, is listed. And calcium-48, atomic number 40. Collide them in a super collider. I made that word up, I'm pretty sure. Still getting over this cold. And then producing tennessine-297, 117, atomic number. And does anyone imagine where is our tennessine at? Does it exist? No. It only lasted for a few milliseconds, 10 to the minus 6 seconds. And it decayed to form a number of different things. This is the decay process. There's a couple of them for tennessine. So which is this is tennessine-297, element 117. The first decay is the loss of 3 neutrons. So to go from 297 and to 294, but keep the same atomic number, we lose 3 neutrons. And then from there, we have several alpha decays to get down to element Db, which is dubnium. Okay. So the first alpha decay, if we go from tennessine-294, Tn-294, which is 117. Again, alpha decay, we lose an alpha particle. And we produce element 115. Again, we need to update these periodic tables. Does anyone know what it is? MC? Another one of these short-lived ones, Moscovium, named after Moscow. And then on and on and on. We won't go through each of those. So, yeah. So that's one of the newest elements produced. There is another one. There's element 118 has been produced. I think that was 20, well, it was somewhere between now and 2010, which is not narrowing it down very much. Does anyone know what it is? Oh, I didn't even write down the symbol. But the element name is oganesson. It's named after a scientist who has worked with forming elements. This is element 118. Some people are really into producing elements that don't last very long. It's kind of really exciting for just a really short amount of time. Yeah. Okay. Questions on any of that? All right, so we're going to have a throwback moment here to chapter 14. We do some rate laws. So this is a great time to recall your kinetics. We're going to look at rates of radioactive decay. That was weird. Rates of radioactive decay. Conveniently, we only have to worry about first order decay when it comes to radioactivity. Any type of radioactive decay, first order, easy. Okay? All right. So we've talked about some radioactive particles that decay very quickly, just like tennessine. Some of them decay very slowly. We're going to talk about carbon-14 and its half-life. The rate of decay has a special term when it comes to radioactivity. Sometimes you'll see the word activity, but also you'll see becquerels. And this is also given a special unit. Anyone know what the unit is of rate of decay for radioactive elements? Named after another famous scientist. It's measured in curies. And it has this, curie is abbreviated CI in this case. So 1 CI is equal to the decay of 3.7 times 10 to the 10. That's a lot of lines. Nuclei per second. And where does that weird number come from? This is the decay rate of 1 gram of radium 266. So it's radium, discovered by Marie Curie. Now she gets a unit named after her, and this unit corresponds to the decay of 3.7 times 10 to the 10 nuclei per second, which is based off of radium. Okay. So you are probably somewhat familiar with carbon dating. So using carbon-14 dating to determine the age of an object, this does have some limitations. First of all, it's limited to a span of time of up to 50,000 years old. Okay. Beyond that, the radioactivity of carbon-14 is so small, it has fallen off so much that you can't detect it. So you could say, okay, this thing is 50,000 years old, but you can't say it's 60,000 years old. There are other types of isotopes that are used to measure other things. So carbon-14 is limited to things that were once alive. Does anyone know why? What's that? Something about carbon. So it has to do with CO2. So carbon-14 comes from CO2 in the atmosphere. If you have a living, breathing thing, it takes in or emits, gets rid of CO2. It's part of the function, right? And so a living object will have carbon that has come from the atmosphere at some point, and that will have carbon-14 in it. But if we have something that has not been alive, has not used carbon in some way in its cycle, for instance, rocks, we can use uranium-238 or lead-206 for that type of dating. I think that carbon-14 is like suspiciously easy sounding. It's actually really difficult to do. And so let's think about the process here. We'll look at our figure, this adorable giraffe. So we have cosmic rays that enter the atmosphere. They collide with atoms and they create neutrons. And those neutrons interact with nitrogen. So when we have a neutron that interacts with our nitrogen-14, it produces carbon-14 and a proton. And that carbon-14 can react with oxygen to form CO2. Well, it's incorporated into CO2, taken up by plants. Obviously, giraffes eat plants. Okay? And people and animals take in carbon-14. Okay. Once an organism dies, dead, carbon-14 ceases to enter into that species, right? And then the concentration of carbon-14 will decrease through beta emission. So that's shown here, right, by that skull. All right, so we're able then to quantify the amount of carbon-14 in a species, and that decreases over time, corresponding with the length of time that thing has been dead, okay? This reaction, okay? So you're basically saying how much of this reaction is left. There's more to it. We're going to go over this lead example, skip over these, and then some examples. I'm skipping. There's a reason, but I don't remember why, but I wrote in my notes not to do it. So we're going to skip over it right now, and we'll go to this strontium example. Okay, so I'm going to challenge you first here to write a nuclear decay reaction for strontium-90, which undergoes some unknown type of radioactive decay to yttrium-90. So the first thing, work with your neighbor, figure out a radioactive decay path. And we'll take a couple minutes and do that. Yttrium is YT, by the way. Oh, yeah, why did I write YT? Senior moment. All right. Everyone think they have an idea of what could happen? There's actually two possibilities. So you could have strontium 90, which is 38, decay to yttrium 90, which is 39, by beta decay. Right? But there's another route that could happen. Could have strontium 90, decay by positron emission, well, absorption. Okay. Both of these are valid. Which one is more likely to happen? Let me ask this question. How can we figure out which one is more likely to happen? Yes! If anyone didn't hear the whispering of excitement, the belt of stability, or band of stability, is correct. So we go back. Amazing. All right. So beta decay is based on the band of stability, beta decay is the most likely route here for our radioactivity. Okay, that's sort of a refresher there for you. Now, let's look at calculating the half-life of strontium 90. And so if you recall, we said everything that is radioactive decays by first order decay, excuse me. And that, if you recall, natural log, I'm going to write this the way we saw it in the past. Some concentration at time t over the initial concentration equals minus k times t, where t is time and k is the rate constant. You recall seeing this? Sure, yeah, I remember that. Well, in this chapter we change it just slightly. So you'll see n sub t for nuclei, number of nuclei at time t over the initial number of nuclei, that's supposed to be a 0, equals minus k times t. All right, so you'll see this type of equation in this chapter. Half-life is the same for first order decay, T1 half equals 0.693 over K. Back in the day, we derived that, and we had a great time doing it. I'm sure you don't remember. But yeah, so these are the equations that we're going to need here to calculate half-lives. So again, radioactive, first order, which is lovely. All right, so let's calculate the half-life of strontium 90, knowing that we have 0.953 grams of strontium that remains in a block that initially weighed 1 gram 2 years earlier. So the question is written sort of in a very backwards way, but basically we have 1 gram block, 2 years happened, and now the block weighs 0.953 grams. What is the half-life? Okay. So if we want to find the half-life, we need to know the rate constant K. And we don't have that, right? But we do know an initial mass, a final mass, and we know a time. So we essentially know everything in this equation except for K, which we can then solve for. And even though we have nuclei n sub 0 and n sub t written in this equation, we can use the masses that are given. Because if we were to convert mass to number of nuclei, we would do the same math in both the numerator and the denominator. And so we can just skip that part and use our masses. Does that make sense? So Let's calculate k. We're going to take natural log of 0.953 over 1. So that's our initial mass, final mass in the numerator, minus k times 2 years. Solving for k, oh, not minus, I'm sorry, there's an equal sign here, just had another moment. Okay. Solving for k, we're going to get 0.024 inverse years. That's what we want, 1 over year. Remember, rate constants are in 1 over whatever time unit. It'll all come back to you soon. It must. It will because it must. So once we have our rate constant, we can plug that into our T1/2 equation and calculate the half-life. Oh, yeah, okay. And from this equation, we should end up with 28.9 years for the half-life. Questions on that? All right. Let's do another one. In your notes, well, write this out here. Let's start with .000 grams of cobalt-60 after 8 years, 0.351 grams remain. Calculate the half-life. So basically it's a similar problem. I'll let you all try it. A couple minutes on that. I'll check it. All right. So just like in the last problem, we're going to use our natural log of n of times t over n sub 0 equals minus k times t. We have everything in this equation except for our rate constant. That's what we're looking for. So then we can use that in our t1/2 equation. All right. So n at time t, again, this is the number of nuclei. But we don't really need to actually calculate the number of nuclei. We can use the mass. All right. And after time t, we're going to have 0.351 remaining. We're initially starting with 1 minus k times, and this was 8 years. And so when you calculate k, you should get 0.131. Calculating t1/2 then, we'll take our 0.693 over 0.131, and we get 5.30 here. How do we do? Good. Excellent. Great work. Should we do one more? We'll do one more. This is the last thing we have. Okay? And it's a good refresher for chapter 14. Okay, so let's look at cerium 131. The half-life of this nuclei is 9.7 days. What percent remains after 45 days? All right, so take a couple minutes, work on this, work with your neighbor. All right, so here we know the half-life. We want to know the percent of cerium that remains after 45 days. So we have T1/2. We have our time that we're going to use in our rate log expression, our rate equation. We want to find n sub t. What can we use for n sub 0? 1 or 100. Yeah, either one. Okay? So let's first use our t1/2 equation to solve for k. K is going to be equal to 0.693 over t1/2. 0.693 over 9.7 days, and we'll get 0.071 inverse days. All right. Then we can use this rate constant in our rate equation, solve for n sub t. So we're going to have natural log of n sub t over, I use 100, so I'll stick with that, equals minus 0.071 inverse days times 45 days. Okay. I did the inverse log, so then I'll end up with n sub t over 100 equals e to the minus 0.071 times 45. Don't forget that minus sign. N over 100 equals e to the minus 3.21, which is 0.040. If we multiply both sides of this equation by 100, n sub t equals 4%. Questions on that? All right, that's the end of chapter 21. I'll see you next time for 23. For now. Like I said, it sounds easy, like, okay, let's just go count carbon-14 in the skull or whatever, but there's a lot to it. There's a number of different ways you can actually perform the carbon-14 dating. No matter what, you have to convert a sample into something measurable. So there are 3 things we'll talk about just really briefly here: gas proportional counting, liquid scintillation counting, and then accelerator mass spectrometry. So in this gas proportional counting, you'll take your sample and convert any of the carbon in that sample to gaseous CO2. And from that, you can measure the amount of beta decay that corresponds with, from there, corresponding that with what we know from sort of like a calibration type of situation. Another form, liquid scintillation counting. Instead of converting the sample to a gas, we convert it to a liquid, which is benzene. Benzene is a ring of carbons, 6 carbons in a ring. And then a substance is added that fluoresces when radiation strikes it. So again, when we have beta decay from that carbon-14, the beta particle strikes this thing that fluoresces, which means gives off light. And then we can quantify the amount of light detected, and that will correspond then to the amount of carbon-14 left. Scintillation, this was a word that basically means light given off. Okay. And then accelerator spectrometry. This is sort of the most up-to-date method, where the sample is converted to graphite. And then using mass spectrometry, you can actually detect each type of carbon isotope, carbon-14, 13, and 14. And so we're detecting isotope instead of radiation. So that is probably, I would say, more accurate as a sort of counting method, because there's not like a middleman kind of a situation. You're counting the number of isotopes. This is the most up-to-date method, like I said. Mass spectrometry is really good at this type of thing. But there's lots of things that go into this. Lots of data and software that you need to actually be able to quantify carbon-14. And something happened in 1955 that increase the amount of carbon-14 in the atmosphere, and it's given away here in the slide. But this is when nuclear weapons testing was started. Okay? And so what you can see in this graph, this is the carbon-14 represented on the y-axis, and then year on the x-axis. And then what is being calculated here is what they're calling radiocarbon or carbon-14 in tree rings in different locations. And you'll see right about 1955, we see this sharp spike in the amount of carbon-14 in the trees. And that is corresponding to when the time when we started nuclear weapons testing. And as we add nuclear particles into the atmosphere, more carbon-14 is produced, more carbon-14 is taken up by plants, and so on and so forth. So it's not just a simple linear calculation to figure out the amount of carbon-14 in a species and then back calculate that to time. I wish it was, because that would be so much more satisfying. But there's a lot that goes into it. I think it's pretty neat. Well, way more than what we need to really be thinking about, but it's cool. There's also reference materials that you need for this type of carbon-14 dating. So you have to have a known value, right, to compare. And I think really the only kind of interesting thing here is that you can buy a standard from the National Institute of Standard and Technology. They're based in the DC area. This is oxalic acid, and though you can't see it, there's carbons right here. And so this would have a known amount of carbon-14 in it that's measured by NIST, and then you can take your unknown sample and compare that to oxalic acid. Okay? And I would like to point out this little price tag right here. 28 grams, you can buy 8 of these samples, and it's going to cost you almost $1,300. So because someone has spent a lot of time quantifying carbon-14 in these samples, it's really expensive. And this is super cool. They have all these different standard materials. They have standard peanut butter. You can buy peanut butter for like $500 from NIST. It's used in, I don't know, whoever is quantifying whatever in peanut butter. They have all kinds of stuff, standard soil samples. Who knows what else they got, maybe standardized paper clips, like I don't know, all kinds of weird stuff. Okay? And it's all very expensive. But NIST is cool if you're looking for a job in STEM. Check them out because they hire a lot of different scientists and they do some cool things there. Okay, let's go back.